a slide window, and the padding of the original inputs decide the output shape. As you can see in the equation, each out is the output size, and each in is the input size. And do notice the shadow here, here, and here. So it's a kernel of convolution as well as the receive field. So since it's only one layer convolution, so the kernel size is equal to the receptive field. Then you must know what the receptive field means, right? It actually means that in each pixel, output pixel here, uh, how many pixels information in the original input image are contained. For example, the darker sign pixel here contains 9 pixels information in the blue input feature map. So the receptive field of this conv layer is this 3 by 3 areas. So as seen, the receptive field is the 4 by 4 shadows here. But only convolution layer is not enough for a good CNN architecture. Some other layers are needed to help in loss converge and training efficiency. So the first one is the normalization layer. Uh, in that, the most popular one is the batch norm here, which calculates the mean and standard deviation based on the blue flags, and then subtract the mean and divided by the standard deviation to normalize the values. Normalization layer usually makes the neural network easier to train and also helps the model in accuracy. There are multiple kinds of normalization layers like the batch norm, layer norm, instance norm, or even group norm. So the only difference between those normalization layers is like how you define a data point, and how that means how you calculate the mean and the standard deviation based on which level or which flat. Okay. The second helpful layer is the pooling layer, which is used as a downsampling method. The most popular pooling method is max pooling, here shows here, or sometimes average pooling. Here, I found an interesting video for you to really understand what pooling does. So as I show in this video, if you can see that it's a original input image, then we pull some grids and put the small grids together to generate a smaller image, which is looks very similar to the original one. Okay, let's back to the slides. Then the last one is the activation layer, which is used to provide the nonlinear capability and also help to solve the gradient vanish problem to make training more easier and stable. There are a lot of activation functions like sigmod, tangent edge, ReLU, switch, softmax, etc. So for now, I will give you a whole vision of CNN. So here you will see exactly what happens in a CNN network. So if you can see, this is the input. Input image is a cup, and with the 3 channels RGB. This is we can see what happens after the first conv layer. This is the first conv layer, right? So if you see the animations here, it shows exactly what we said, how to compute the convolution. Then it's the activation function value here. Right, if you can see that it's just reset all the negative values to non-negative one. So this seems all the non-active. So if you see this example, these are all negative values, but all will be set to zeros. The same thing happens in the next conf. Uh, and this is map pooling there. Just what we discussed in the previous slide. Downsample the input from 60 to 30 to 30. Okay. Then this is the normal neural network, also named as linear layers. It's just a simple weighted sum plus a softmax activation function. So you can see that how CNN network is worked for to solve the classification problems. Okay, let's back to the slide. Now, I believe we all know what exactly happens in CNN forward computation. Then the question is, how can the network learn from training data set? Yep, the answer is supervision and gradient descent. All of the kernels, uh, these kernels in conv layers and weights in the neural networks are all learnable parameters to make the network predict more similar output compared with supervision. And the gradient descent method will help to find those best parameters. So this gradient descent method are also called optimizers. Here I showed you 5 different optimizers: SGG in cyan, momentum in magenta, 88 gram in white, RMS pros in green, and Adam in blue. As you can see, Adam is the most fast and accurate optimizer in this situation. But it actually depends on the loss functions and the dataset distributions. Adam may be the best optimizer for the new joiners because you don't need to tune too much hyperparameters for it. But actually, a lot of state-of-the-art models are trained based on SGG. So if you are familiar enough, then SGG is also a good choice for you. All right, I guess we almost know all about the basic theories about CNN, which is key component of nowadays computer vision field. Now let's move to the next part, computer vision in the industry field. Here in Shopee, we use different kind of computer vision techniques to solve different problems. For example, image search. If you open your Shopee app, click the little camera on the top and take a picture of any product around you. Then you can search the similar products on Shopee to see if there are any cheaper and better options, or a product classification system to help us manage a huge number of products in Shopee. This time, you guys will help with this. Another application directions might be the security. Uh, Face recognition and text OCR were used to protect every user's account. And also, we use image segmentation techniques to improve our user experience, as you can see in this picture. So basically, there are a lot of scenarios where we can use computer vision techniques in industrial field. Above examples are just some of them in Shopee. Not to mention there are lots of scenarios in the applications that like auto drive or movie production. Then I'm going to share some common pipelines on how to start a project from my point of view. Basically, when we receive a request from a customer, we need to and model related part, and also product related parts. So in data related parts, including the data fetching and image preprocessing. For data fetching part, we need to mainly consider that whether we sampled data is a fair data set and the distribution we sampled is good enough to present the real world data. For data pre-processing, we need to do the noise because the real world data is usually much more dirty than you think. Then we need to properly sample data to deal with the unbalanced problems, or you can see it like the long tail process. For model related part, we need to firstly decide which kind of task scope uh, we will use. That means identify the task scope. So which kind of models we're going to use, classification, detection, segmentation, or 3D reconstruction, or even all combined. Then we need to do the research on the specific field to find the SOTA algorithms to see how to build a perfect model on this field. Besides, after we build a model, we will need to evaluate the model performance based on the real scenarios. If the statistics support that this model is ready to go for production, then we will go for the next step to production. Otherwise, we need to check the reason and restart the procedures all the way. For the production part, like we discussed, if the evaluation passed, then this model will be used in our live services. So basically, that would be a common pipeline for you to start a project. Now we're going to a little bit deeper to discuss some data-related problems in computer vision or even machine learning. In the real-world dataset, we must think of data fairness. So what is data fairness? It's related to the data distribution. Considering that recently face masks have become much more popular than before. You can see them everywhere on Shopee app. However, hardly can you see a down jacket on Shopee app, since people who live in our region usually do not wear them. So there are not very many of those kind of products on Shopee. So the face masks will be called the head classes here, since it has more samples. Um, while the down jacket would be called the tail classes, since rarely can we see such images or data. The models you build are expected to have equal performance for head classes and tail classes. But it's unfair for the tail classes since the exposure of those are much less than those of the head classes. Yeah. So which one should be right? The most popular product counts more, or we should treat every class equally? And how to deal with the tail classes or even unseen classes? I think for some reason, uh, all products should be equal. Firstly, it will keep the dataset diversity. Secondly, we cannot predict that those tail classes uh, won't become popular in the future, just like the face masks, which I believe were part of the tail classes on Shopee 1 year ago. All become because of the COVID-19, it become the most popular products in Shopee. But it still should decide by case by case. In some special cases, we still might have to sacrifice the tail classes. Then how to solve the problem? I think a sophisticated sampling method might be needed. in this method help us to find some representative samples for the head classes that reduce the head classes number to downsample them, while upsample the tail classes by different kind of augmentation techniques. So by that means we can kind of solve the unbalanced data set. This is just one possible solution. There might be some better options instead, but we won't discuss too much about this. So here I'm going to give some examples about noisy and unbalanced. In this page, all of the images are labeled as corn actually. They're from the same classes. But the central one is actually the green beans. So it's a noisy data within this class. Or in this example, all images are labeled as wine. However, the central one is actually the rice one. So it's another noisy data. Both examples are wrongly labeled. Here showed an example of unbalanced data set, or you can see it's a long-tailed distribution data. Some of the classes have more than 1,000 samples, like the portrait here, while some of them have less than 100 samples, as you can see the water snake. In a real system, you even need to process those unseen categories to make your system scalable, as you cannot, since you cannot retrain the model once you have a scene class. All above are key factors that need to take care of, or at least consider it when we start to process the data. After data related part, we need to choose the task scope. Actually, there are so many task scopes in computer vision, but here I just list some of the most popular tasks. See, the data unfair is just everywhere, right? That's why data fairness matters, right? So I listed here classification, detection, segmentation, and 3D reconstruction. In this workshop, due to the limited time, I am only able to discuss the classification and the detection. But I think these two tasks are also the big foundations of the other two. So I hope in the introduce on the classification and detection can also help you to understand other tasks as well. So let's start from the classification model. Or we also call such classification models as backbone models, since they are so important to other tasks. So basically, this round of deep learning started partially from AlexNet in 2012. It proved that deep learning CNN models can perform much better than previous manual craft era. From then on, a huge amount of sophisticated CNN architectures were proposed with a significant performance improvement, like VGG, Google Research's Inception, and Facebook AI Research's ResNet and ResNext. They are all manual designed CNN architectures. And at that time, people believe the deeper and bigger network, the better performance it will get. So I call it a manual design and heavy era in the blue zone of classification backbone evolution. Until 2017, Google Research proposed MobileNet and proved that we can design a much lighter network to get the same level of performance. And such a network is extremely suitable for mobile devices or edge computing. Then in 2019, Google and Facebook proposed EfficientNet and RedNet respectively, both based on NAS, which is network architecture search. This means the architectures are no longer designed by human, but instead generated by the machines. So it's the NAS and light era. Or even better, I would like to call it the auto machine learning era in the yellow zone. Okay, let's quickly go through them one by one. So AlexNet is a 8-layer CNN network, and it's first introduced ReLU as the activation function in CNN, which is widely used in the afterwards works. Then the VGG was proposed by the University of Oxford and got the second place in the ImageNet competition in 2014. VGG network has 16 layers or 19 layers of convolution of neural network. And from this work, the 3x3 convolution kernels is widely used. And this work gave insight that the deeper and the network is, the better performance you got. Then the inception was proposed by Google Research. It proposed to use spatial separable convolutional and one-by-one convolution for efficiency. Basically, what they did is to replace those 3x3 or 5x5 convolution with 1x3 and 3x1, or 1x5 and 5x1, and plus a 1x1 convolution. By doing this, the the size of the feature map keeps the size of the feature map keeps the same, but the computation resources reduce a lot. Meanwhile, it provides a new dimension of CNN architecture, which is cardinality. Before, we only measured the neural network, the CNN network on width and depth. So what is cardinality? It's actually branch here, the branches here, right? There are, for here, we got 4 branches here. So the cardinality is 4 here. So it shows that more branches will give better performance. So it's understandable since the more branches means you get the more sophisticated feature extractor. Then in 2015, Facebook AI Research published ResNet, which is a milestone of the CNN. It's using the shortcut connection to build the more than 100-layer network and boost the performance as well. The deep learning becomes real deep learning from that time. ResNet is so promising that a huge number of researchers are based on their shortcut connection idea. So now ResNet has already become a network family, including ResNet 18, ResNet 15, ResNet 101, etc. And since the ResNet family has a good transfer learning capability, and it supports very well in PyTorch framework, it becomes one of the most popular backbones. Then we come to the manual design and light era. In 2017, Google Research published MobileNet and proved that the small network can also have the not bad performance. A small size makes it very popular in the edge computing field. They use the depth-wise separable conf to reduce the number of parameters. As you can see, this is the MobileNet architecture, and this conf DW is the depth-wise convolution. Then, in the last 2 years, we came to NAS and light era. EfficientNet with a very small number of parameters to achieve the SOTA result on ImageNet to depth-wide convolution, and provide all sizes of network from edge computing to heavy GPU services. To achieve that, the, they define three dimensions of scene architecture size: the width, the depth, and the resolution, which is the input image size actually. And they designed a method to effectively scale up the dimensions, three dimensions together to get the better performance. It also shows a good transfer learning capability for the efficient net. A few months ago, March 2020, Facebook AI Research published the RegNet. It actually shows the paradigm that how to use the NAS to elegantly design a network architecture. And another big contribution is that RegNet is 5 times faster than EfficientNet. You know, the EfficientNet already has a very little parameters, but RegNet with more parameters and even more flows, but it's still faster than EfficientNet. Why is that? That's because depth-wise convolutional is actually um, do have the less parameters, but they cost much more I/O. So the bottleneck of convolution of depth convolution is no longer the computation, but instead the I/O. Above all, we basically introduced some popular and important CNN backbone networks. Then we are going to move to an object detection system. Here is a graph shows how the detection system evolves through the past few years. It firstly starts from RCNN, which is a simple but effective idea to use the slide window to select a proposed region and then use a classification model to predict the categories. Since this model needs first find the proposed region and then classify the object, so it's called the two-stage method. This two-stage method was improved a lot through the fast RCN and faster RCN. These types of detectors have a very accurate but a little bit slow. It's not suitable for real-time applications. Then YOLO came to us. You only look once, which means it removes the region proposal step. Instead, YOLO used anchors and channels in conv layers to predict class and regress the bounding box in one step. So this kind of method is called one-stage detector. So it's actually a very smart idea. So the two-stage detector is kind of straightforward, but one-stage detector is really a great idea. So SSD is another brilliant one-stage detector. But recent years, YOLO took more eyes due to its active community. You can see the YOLO system is evolving very fast and quickly. So the biggest foundation of detection system are built by two-stage detectors and one-stage detectors. Besides, researchers also noticed that the multi-scales helps a lot in small object detection. So the pyramid scale was also introduced to the detection system and serves as a basic component. Recent years, researchers focus more on how to combine the one-stage method's efficiency and two stages accuracy. Some good work has been published, like RetinaNet, CornerNet, and FGOS. Okay, let's go into some popular detection systems. So firstly, I'm going to introduce the classic fast RCN. region proposal network to propose and predict whether there are interested regions and propose those regions in interest to the upper classifier or regressors to predict the category and bounding box. Note that here the ROI pooling is not the same as we talked the max pooling or average pooling. So this ROI pooling is used to keep the input feature maps as the same sizes. So if you can see in the proposed regions, the size might be different. So we need the ROI pooling to make the output of the proposed as the same size. So like I said, fast starting is a two-stage detector, and it's anchor-based. And this detector is very accurate, but a little bit slow. Then we come to YOLO. As you can see, the YOLO architecture here is quite similar to the classification model, since it's very simple and one stage, only conf layers, background layers, and value layers there. It splits the feature map channels into two parts. The first one is the channels that save classification information, and the second one is the channels that save bounding box information. And each grid in the feature maps will be responsible for an area, or let's say one object. By doing so, we only need to use the CNN network to predict the both bounding box and categories. So these three branches I use the FPN to prepare the multi-scale like we discussed previously. So YOLO is still anchor-based and it's very fast and suitable for real-time application. While the accuracy is slightly lower than two-stage detectors. But actually with multiple scales like FPN support, recent days, YOLO V3 or YOLO V4, even YOLO V5 shows a great potential on accuracy. Here we come to FCOS, which is a one-stage detector, and it's anchor-free. The motivation of such anchor-free detectors is to try to combine one-stage detectors with the two-stage detector and make the best use of the two methods. Okay, after all those things related to theoretical stuff, I will introduce some useful frameworks to help you implement your competition or future project. So the first one is called the augmentations. It's a useful and fast image data augmentation tool. It supports various image processing methods like RGB shift and channel shuffle and random contrast. Is that true? It contains more transformations than Torch Vision packages, which is the PyTorch official image processing package, and even faster than Torch Vision. Second one is the called PyTorch Vision or PyTorch CV, which is a useful backbone model zone, and it supports various latest model architecture in PyTorch. Like we've mentioned before, the VGG, ResNet, Inception, and even the latest Efficient Lab, you name it. You can reuse the backbones and start your transfer learning easily by use this package. This will be very convenient for you to start an image classification task from this. Okay, the last but not the least is the popular detection framework, detection tool from Facebook AI research. You know, as I said, detection is more like a system instead of an algorithm. So a good detection framework will help you will help you really a lot. Like you don't need to handle the annoying post-processing part, like NMS, which is the non-maximum suppression. You don't need to handle the data format conversion from one to another, things like that. So you can only focus on the model architecture benchmark. Meanwhile, detection tool has a big influence in the computer vision field. So various detection algorithms are now starting to support the detection tool version to let the researchers easily use and study. So it's a good opportunity for you to start detection from the detection tool. Besides, the community is quite active. So you can search for a lot of documents and resources about detection tool. And I think you will be get familiar with it quickly. All right, above stuff almost includes all of the topics I showed in the overview. Now I'm planning to give some bonus to you for your listening and support. It's about some training tricks that are proven to be useful in various computer vision tasks. So I divided the training tricks into two parts. The first part is the related to the data augmentation, including cutout, hash, grid mask, mix-up, and cut mix. The second part is related to the training strategy, like label smoothing, learning rate warm-up, etc. So let's go deeper with it. This is the cutout augmentation. It's actually randomly removing a rectangular area in the images. It will make the model more robust and get attention to other areas. So this one might be more clear. So the hash, which is hide and seek, it split the image into x by x grids and randomly remove the, the grids in each epoch. So it's much similar to the cutout. And here you can see after removing the some parts of the image, the attention starts to shift to other parts of the image, which is also an important feature we cannot capture from the original image. Then is the grid mask. Instead of randomly removed, a mask will remove all of the grids on the different scales. As you can see, there are three scales in this demo. So almost the same effect. It will reduce the overfitting problems and make your model more robust. Above some methods that remove partial images, there are also some methods that directly combine different images, like mix-up. It combines two images on pixel level. It's a weighted sum, a simple weighted sum to get the new image like this. You can see. So this is a image one, and this is the image two. Then after the mix-up, we got this final image here. Do note that if you use this method, the loss should also be weighted by the same hyperparameters lambda. Okay, there are also methods that need both remove and replace. This is the cut mix. It's actually the combination of mix up and cut out. It first removes a part of image and then replace this missing part with another image. So like this. So if you see in the table, actually by using the cut mix, you can get around 1% for the accuracy on the public data set. to gain some accuracies. Then we come to training strategy method, label smoothing. Unlike above augmentation tricks, label smoothing is not require any manipulation of images. So it's just transforms your label from hard to soft. Here the alpha is the hyperparameter to control uh, how much soft you want to the label to become. If alpha equals to 0, then we don't use the soft labels at all. Then if the alpha equals to 1, then all categories labels are the same. Oh, the key here means the number of categories. So consider that if you have a binary classification, then you set the alpha as 1. Then all of your labels will become 0.5. So it's better for you to control the alpha hyperparameters to decide how to use the label smoothing. The label smoothing is used when loss function is cross entropy. It will help you to denoise the data and reduce overfitting to some extent. Then that's all about the tricks I'm going to discuss today. There are countless tricks that you can further explore, but do note one thing that all of the augmentations will mm, help your model performs better in most cases, but it will still depend heavily on the different data set. So you will need to do a lot of benchmarks and experiments on the different data set. Okay, and that's all for today's workshop. Thanks for listening. So, so let's start the Q&A session. So I will pick a few questions to answer. So please type your questions through the Q&A. Okay, sorry, I need some time to read. Mm. So I thought let's choose questions. Should we detect several objects in every image of product, or we only need to detect one object in the image? Okay, I think it's actually related to the computation, right? So in our computation, it's actually nothing to do with the object detection. So it's all of the concept is about the image classification. You only need to build image classification models. Okay, let me pick another one. Mm. So what's the SOTA algorithms? All right, so the SOTA algorithms is based on which is actually determine which data set. So if you mean the ImageNet, then you can search for some the latest papers like the RegNet and the FishNet. As I showed in the previous slides. Um, yeah, I think currently the SOTA algorithms are the RegNet or even the latest one, the ResNest or something like that. But that is really depend on different data set. I guess for our scenarios, I mean, it won't uh, have too much difference between those sophisticated CN architectures. Mm. Okay, another another question is like, may I know how to read the data from the unzipped image file into the code? Also, is load data able to read JPEG images directly, or must it be a form of CSV file? What do you mean by that? Uh, actually, the data set we provide is just the CSV file for you to index the file, the image file, and we to as an index for you to search the specific image file. So that is what the CSV file use. And do remember that when you submit the result, you need to based on the text.csv file instead of the files inside the text folder. All right, let's pick the last questions. One last question. Mm, okay, so another question related to the computation still. So can we use the pre-trained models for the computation? So actually, you can use the pre-trained model from the open source dataset, trained based on open source dataset, like such like the ImageNet or Pascal VOC. The dataset like this, the pre-trained data model is permitted. All right, so let's go back to our slides. Okay, so I guess that's all for today's sharing. And to remember that stay connected with us on our social media platforms, Instagram and LinkedIn page to receive the latest updates from Shopee. And thanks again for your listening. Yeah, and do remember that please take a minute to do this feedback form. Your feedback is greatly appreciated. We will leave this slide for 5 minutes. Okay, thanks for listening.